That's a good thing. Okay. Yes, I do apologize. There's a tiny part where these haven't been recorded, and so for posterity, I just want to quickly show that just basically what we did in the first slide is saying that if we consider the potentials, whether it's the scalar potential or the vector potential, we can express electric field and the magnetic field in terms of potentials, which are then both governed by so-called Poisson equations. Or if you're in vacuum, then you consider Laplace equations. And so what we want to do in this lecture is to consider the Poisson and the Laplace equations, in particular, how to obtain solutions from them. So for example, if you know what the source distribution is. Okay, so if I ask the following question, okay, so in this case, what is the solution? Now this should be a very easy warm-up exercise, but I want you to at least take a quick second to think. Okay, faced with an equation with a one-dimensional Laplace equation, how would I get the solution, and what would be the solution? Okay, I'll give everyone a quick second. Okay, quick second to think. Harry and Kelvin more or less give the same solutions. So it says ax plus b or k1x plus k2. Indeed, right? So this is something that if I simply integrate left, right twice by with respect to x, I simply end up with a form that looks something like this. Phi of x equals mx plus b. In this case, really what is there to note is that this is a straight line. With two unknowns. Okay. So the characteristic of a one-dimensional Laplace equation is that we end up with straight line solution and then with two unknowns. Now, just as a quick kind of primer, do you know, or can you think how this how to get to constants? Okay, again, I'll give you 2 minutes to think about it. But faced with a question like this, how would you get m and b? Okay, I see a lot of answers rolling in. I see people talking about initial or boundary conditions. And our Ming initial conditions is for t equals 0. There is no t in this equation. So indeed, right, some of the answers that I've rolled out here are indeed what we need. Whether you call them initial conditions, where you use the word initial for the temporal, or use boundary because you're talking about space, is not too relevant, right? I could have simply replaced x with t and talked about initial conditions, or I could say, okay, this is x, and then I can talk about boundary conditions. So indeed, boundary conditions. But what does it hold? What does it mean? Right? Talk about a boundary condition. Can someone give me an example of a boundary condition? Okay, so Ao Chapming says electric field tends to 0 to infinity. That's too specific, right? Let's just consider the maths, and in particular this 1D Laplace equation. In order to, what can you give an example of how I would get M, how would I get B? Wow. Harry, how do you write the phi in text? Never seen that. Excellent. Okay, so for example, Wing Ching. Yes, Jesse. Um, as for example, you can look at phi equals 0. Phi at 0 at x equals 0 equals 0, right? But that's simply 1. And then Kelvin is saying phi or phi prime at a particular x. Okay, okay, I see things rolling in. So those are all good ideas, right? So Jesse says, putting give a particular phi at a particular location. That's good. And Kelvin actually adds something here which says phi prime is also a possibility. So not just looking at the specific values of phi, but also looking at the derivative of phi. Okay, next question. This should be fairly simple. How many boundary conditions do I need? Okay, Harry says 2 for 2 unknowns. Good. So in this case, I need 2 boundary conditions. Okay. So again, try this at home. But if I specify either the 2 endpoints, okay, phi at x equals 0, and phi at some x equals to 1, and then the values, and then I specify both m and b. But the same thing would hold if I specify, for example, the derivative. Okay? So indeed, we need 2 equations for 2 unknowns. Very good. Okay, so that's something, right? That's something to keep in mind. And we can actually apply the same thing when we talk about higher dimensional Laplace equations. Let's consider now some generic n-dimensional Laplace equation. Okay. And this then becomes a partial differential equation. Partial differential equations. Okay. For example, in 2 dimensions, I'm not going to write the full set of n-dimensional, but this is x squared plus partial phi partial y squared equals to 0. So this indeed, it relates an unknown function of two or more variables to its partial derivative. Partial derivatives. So this basically gives me a handle on n dimension, right? So instead of making an ordinate differential equation, I'm now considering partial differential equations. And so how would I get a solution of this equation here? Okay. Now, of course, from the onset, you may think, okay, well, but this is not necessarily a very easy thing to do, because now it depends on two or more variables, right? So phi here, in this case, phi equals phi as a function of x and y. Now it could go in this direction, it could go in that direction. And can we get a general solution for something like this in the first place? Okay. Now, generally, this may or may not be the case. Don't know. So that's something that we need to study. And it turns out for certain classes, it is possible, just like in the one-dimensional case, to get a general solution. Okay, and so if I consider v phi of x and y such that uh, x and y is written as a single variable. Let's call this p. Okay? So in a very similar way to what I've tried in a one-dimensional case, where I'm trying to come up with a very generic solution, right? Mx plus b. I can try to do the same thing in the most general case for the n plus equation. And so one thing that I could do is I could look for solutions, phi, x, and y, such that I can basically write this as a phi only as a function of p, a single variable, which of course a single variable itself could be a function of x and y. So as an example, I could ask, for example, phi xy equals to x to the fourth plus 4x squared y plus y squared plus 1. Okay? And so in this case, and this is again, I'll give you a minute or two to think about this. Hopefully you have a pen and paper ready to play along. But is it possible here to write phi as a function of xy in terms of phi as a function of a single variable p? Okay, I'll give people a minute or two to attempt to see if this. I was just about to say. Okay, does anyone else have other solutions? Okay, so Ao Ming is saying that I can rewrite this so correctly, that I can rewrite this as x squared plus 2y squared plus 4. So then I can just simply change this into squared plus 4. Just phi as a function of p. Okay. So under certain circumstances, this is possible. And so the question is, can we generalize this? It's something that we can, you know, guarantee ourselves that this would be possible, or at least under which classes is this possible? That's going to be the challenge for after the break. I want to institute a quick break here. In the meantime, let me leave you with another one. Sine x squared, sine x squared cosine 2y plus cosine x squared sine 2y. Okay, so can I rewrite this in terms of phi as a function of p? But let's take a 5-minute break. So we come back at 5:07. Okay, everybody in a minute. Okay, I think we can get started again. So let me first get to Harry's questions. Harry's asking whether there's a minus sign on the right-hand side of the first two equations in the first slide, and he is correct. So minus sign here and a minus sign here. Okay, well spotted, Harry. Okay, anyone has an answer for this quick question here in the middle, in the bottom? Still awake? Equals x squared plus 2y. Sine. So consensus here more or less. Everyone's answers being some form of x squared plus 2y. And indeed, Jason says it's a sine. Right, sine x squared 2y. And we've got phi as a function p. Good job. Okay, so it is, under certain circumstances possible to write something very generic. And let's see if we can even make this even more generic by considering the following. Okay. Now, again, let's consider general solution. Okay. And in this case, let's consider with the ansatz first. Assume there is a p equals p as a function of xy. Okay. Then, of course, the partial derivatives are given by the following. Partial phi partial x equals, and then I can use the chain rule, d phi dt partial p partial x. And similarly, I can write partial phi partial y equals d phi p partial p partial x. Okay. Indeed, our assumption is that there's a p such that phi equals phi of only p. So assuming or given, again, let me write Poisson equation up here. So it's partial x phi plus partial phi partial y squared equals 0. So what I want is that, or one thing, if you look at the structure here, especially if you look at the two, first partial derivative, is that we want only d phi dp squared. On the left-hand side, where we have the second derivatives of phi, we ultimately only want d phi dp squared. Okay. As to phi, and that's because the right-hand side 0, and so all references of phi can be cancelled out. What do I mean exactly by that? And that is, I want something that only the the only reference to phi is being the d phi dp, such a way that then I can take it out of the common factor. Since the right hand side equals 0, that cancels out, and that gives me the only thing that is then left is a relationship between p and x and y. Because that's the thing that I'm looking for. I'm looking for, is there a general form of the solution that does not depend on phi? And then I can get p as a function of x and y. So that's the goal. Let me illustrate this even more carefully. The second derivative, second partial derivative, gives me the following. So for example, if I do partial x, partial phi, partial x, okay, that is simply partial x of d phi partial p partial x. Then again, I can rewrite this as this properly. So first I use the chain rule. Here I get let's partial p partial x by dp squared plus, in this case, this is by dp partial p squared partial x squared. Okay. Now, so remember that I only want this to be the reference, right? I only want this term to survive here. I don't want any other term with phi. In that case, I can take it out of the full equation, and I can get something that only depends on p and x and y. So in this case, we want this term to disappear. Vanish. How do we get this term to vanish? Okay. Assuming a very general phi. Well, we can do this by requiring that partial p partial x squared equals to 0. And of course, I can do the same thing for the y, if I do the second derivative of y. This then ultimately leads to partial p partial x equals some constant. Same goes with partial p partial y. Okay. And so here, if partial p partial x and partial p partial y equals to 0 equals to a constant, end up with something that then looks like p equals ax plus by. Okay, I hope that is clear. And so once I have this, once I know that I've got, for example, I've got p equals ax plus by, well, then the Laplace equation gives me that partial phi partial x squared equals to a squared dv squared and the partial v partial y squared equals b squared d. And then ultimately, I can write a squared plus b squared equals, oops, ab squared equals to 0. Okay. And this is something that we can solve, because assuming that dv dp is not generally 0, I have to have whatever is in the bracket equals to 0. Or in other words, I need to have that b over a squared equals minus 1, or b over a equals plus minus I. Altogether, we have that phi as a function of x and y is just a function of x plus iy plus g, another function fi minus, x minus iy. So as you can see, it is in general possible to write something that is, that gives me a general solution to this equation. This is a general solution. Okay. But still, we have two functions that are unknown. We have two functions. The only thing we know is that one of the functions depends on x plus iy, and one of the functions depends on x minus iy. And so if I can write this in a generic form like this, then this would automatically be a solution to the Poisson equation. Oh, did I write V again? Yes. Why do I keep writing V? Right? I'm used to writing the potential as V. Oops. And oops. And phi. Oh no. Phi, phi, and phi. And this is a phi. Here we go. Well spotted. Okay, so indeed, it is possible, but the only thing that we're left with, as opposed to in the one-dimensional case, we are left with two arbitrary constants, e and n, right? Just whatever defines the slope. In higher dimensions, we can still write a general solution, but now we have the two unknowns here are two unknown functions. Here and here is two unknown functions. Okay, just as a reminder, if you have questions, please do send it out to everyone. Don't just send it to me privately, so that I could respond to it, but people would also know what the actual question is. Okay, again, I'd be happy to take questions, but please do so in public, so that this would help me. So, Pun Shenqi, can you type your question? Can you copy your question and put it in the Okay, so the question is there a typo in the last slide, which should be dx squared in x? Yes, did I not write squared? Oh, the squared here. Yes, you're right. Yeah, that should have this factor, this factor, this. Okay, at this stage, I really want to commend everyone for their quick pace. I don't think I would have been able to spot this if I was listening to a lecture, but well done. Yes, this is correct. This should be squared here, because you get 1 from taking the first derivative, which is here, and then you're getting another one for when you try to differentiate this with respect to here. And then you get another one. So this would be 1, and this would be 2. Indeed, well spotted. Okay, let's move on. Now the question is, again, instead of 2 constants, we now have 2 unknown functions. And again, these 2 unknown functions are then going to be set by what? What is going to set these 2 unknown functions? Boundary conditions. Very good, indeed. So again, we end up with a similar. We end up with a similar structure where we have a general form of the Poisson equation, and then we get to further specify it by the boundary conditions. Okay, and so this is really where the key point lies, right? When solving the Poisson equation, or when solving the Laplace equation, the thing to note, the thing to bear in mind, are the boundary conditions. That's going to be the important key. And so, since this is such an important topic, let's see if we can first generalize this. So let's take a quick look at the type of boundary conditions. Type of boundary. This is super ugly. There's no, by no means say conditions there. Okay, so there are different types of boundary conditions, and this is just a little bit of jargon, so bear with me. And so for second order derivatives, okay, for second order, okay, boundary conditions involve specifying phi, which is our scalar field, or and some of its derivatives. Okay. And in particular, these are the types, and these are not all the types, but these maybe are common types, are the following. So we got the Dirichlet conditions, basically says that the values of phi are specified at each point of the boundary. This is important, right? Again, because we're no longer in 1 dimension, we have to consider the entire boundary. In 2 dimensions, it's going to be, some boundary to some surface, right? And so the Dirichlet condition basically says that the value of phi are specified at each point of the boundary. Okay? And then we also have the so-called Neumann boundary conditions, which says that the values of some derivative, okay, let's call this partial phi partial n, it's just the gradient of phi dotted with some n, normal to its surface, so it's the derivative normal to phi, again, is specified at each point of the boundary. Finally, there's also a Cauchy class of boundary conditions, which says that both phi and the gradient of phi multiplied with n hat are specified at each point. At each point of the boundary. Okay? This is just a little bit of technical jargon, but it is important once we, if you want to take a look at a very formal structure in terms of the mathematics, is okay. We have got the Dirichlet conditions, the Neumann conditions, or the Cauchy class. See that the Cauchy class is more stringent, right? Both phi and the derivative of phi are defined with respect to the boundary. And so what we'll see is that, of course, not every type of partial differential equation requires, as stringent of a boundary condition as the Cauchy conditions. Actually, generally, we'll see this in more detail later, is that we need the Dirichlet condition and the Neumann condition. Okay, but this is what we'll do when we get to the topic of uniqueness theorem. Okay, when can we uniquely identify solutions to the Poisson equation? And there we will see that we will either need the Dirichlet condition or we need the Neumann condition. Okay, so before I go into looking at the particular solutions of this, I wanna first take a step back and take a look at, okay, what are the boundary conditions for the electrostatic field and for the magnetostatic field. Okay, and so that's the next thing that we'll look at. But we are going to go for a quick break. But during the break, let me at least leave you with with something to consider for yourself. So imagine that we've got some slab of, you can make it a conducting material, and indeed this slab has some surface charge. Okay? Surface charge like this. And then the question is, in this slab, if I take a look at the side view, which is this thing here, this slab here, then what are the values for, let's say, the electric field above and the electric field below? So above and E below. Okay, if this is some sigma here. So that's what I'll leave you with. It's 5:30 now, so let's take a 5-minute break. We'll come back at 5:35. Okay, see you guys in a bit. Okay, fully reviewed. Let's get started. So I've given you this little problem that we're going to take a look at now. But I asked you to take a look at it over the break. So hopefully some of you will have done so. Let me get rid of this stuff. A little bit more nicer to look at. Okay. So let's get started. So let's take a look at, boundary conditions. Boundary conditions in particular for the E field. We have a charged surface. Charged surface. This is density. So let's draw a surface like this. And indeed, we are interested in looking at, okay, well, I have this division line, which is the surface from the side view. And we're interested in, this is E above, this is E below. So the first question is then, how would you be able to, relate what is E above and what is E below? Anyone have a clue? So even in general, right, we've seen it in the first problem set already, or the first, yes, or is it the second? Maybe the second. Anyway, first one or two. So if I have some particular charge distribution or total charge, then how do I get, the field outside, or the electric field outside? Right? This is something that you should have seen the 2041 as well. We can make use of two things. What are the two things? What do you guys think? Okay, which law can I make use of? Gauss, indeed, Gauss's law. Okay, very good. So indeed, what I could do is I could create an imaginary surface over which I'm considering, what is inside. And so let's construct one of these surfaces. Let's take a look at, draw something like this. Okay, and then that is going through underneath here, here. Okay, and this here is, enter like this. Okay, this is quite awfully drawn. Not very good. As you can tell, my drawing skills are not very up to snuff, but we'll just have to do. I do like to have at least things correct in like a three-dimensional sense. Freehand. Okay. I'm creating a surface like this. A little bit like this. Arguably worse, but okay. And this is the midsection here. So from the side, how does this look like? From the side, it looks like something like this. I've got a box, that goes in and out like this, and pierces through this surface, and then I can simply use Gauss's law. In this case, do I have that Gauss's law dictates that the integral over some closed surface dot ds equals total charge enclosed over epsilon naught. So what happens if I now make this I let this thing here, and let's call this eta. If I let eta goes to 0. Okay? So the height of this box, I'm going to let it go to 0. In which case, I only have two surfaces left. I call this surface A, size of this surface, the top surface. So if I let eta go to 0, then only the top surface and the bottom surface survive. And then I can do this so-called integral. I can do it kind of by hand, because I could consider all of the surface individually. Let's consider the top surface. In this case, the top surface. Drawing again. I'm going to stop the share first. And okay, let me pause the video and recording. Okay, welcome back. Technical thing done. So indeed, we have the top surface, and there I know that the total surface is A, and I also know that E, if this is this charge is uniform, then A either points up for the top surface. So in this case, A and E are in the same direction. I basically get that for the top surface, I have E above, this one, I have E above times A, and then the bottom surface below times A, and in this case with a minus sign, with a minus sign. I want everything to be minus sign, because field would go in one direction. Okay, and so in this case, what do I have? Well, I have that the integral here, okay, the sides go to 0. So the total, the integral, it becomes E above minus E below equals, sorry, this times A equals, and on the right-hand side, we have to look at the total charge enclosed, which we can write as sigma is the charge density times the area over sigma naught. In this case, by construction of the way we created this box, we are only considering the component normal to the surface. So the first boundary condition that I want to state is indeed that E perpendicular above minus E perpendicular below equals to sigma over epsilon naught. Okay, so in this case, from this equation to the other, from this equation to this equation here, I've simply divided out the area that I'm using. So this is my first boundary condition, and that is that the perpendicular component of E, is discontinuous over some charged surface. So Pun Shen Chi is asking, is it assumed that there's some external field? Well, the field is generated by sigma in this case. Okay, so there's some charge density over at the surface. And so if you think about it, this is often something that you see in common situation where I have some surface where I know what the charge density is. And so in this case, I can actually specify what is the electric field below and what is the electric field above. And showing here in this case, we show that there is some discontinuity in the electric field. Okay, and the discontinuity is proportional to exactly what the charge surface density is. Now that's one of the boundary conditions. And then you may ask, okay, in that case, what is the parallel component to the surface? Okay, we've only had now the perpendicular component to the surface. What is the parallel component to the surface? So we can do the same exercise. And let me draw out the surface again. And so in order to get the parallel component, we do, well, we can, instead of a box around the surface, I can actually do a loop. Do a little loop like this. This is the middle. Okay, this is okay, so there's a question from Yip Choi Ko. Anyway, Yip Choi Ko, let me quickly try to fix this very awful drawing before I come to your question. Okay, so the question is, if the field is due to sigma on the surface, why the field lines above and below are not pointing in opposite directions? They are pointing in opposite direction. Due to sigma on the surface, why shouldn't it be symmetric? Yes. I'm not entirely sure that I understand what the question is. Okay, maybe we can do this at the end of the lecture. I'd be happy to maybe spend a little bit more time. It may be a little bit too rushed to type everything in. Okay, so let me try to finish this this part up, and then we can defer this question to the end. So let me try to finally learn to draw for once. Can't be that hard, can it? Here we go. That looks more like it. Okay, so instead of now doing a box, I want to do a loop. Now the loop does cut through this surface, right? So this line here is roughly the surface. And so if you want to take a side view, take a side view here, then the loop that we're considering is something that would go like, it comes, let's say, in towards us, comes towards us, goes away from us, and then there's a line, of course, that then goes this way, where, we could say the integration goes from here towards us and then away from us. Yes. So this could be the integration path as well. And so in this case, what do I know about this? Well, I know that E dot dl around a loop equals to 0. So again, if I let this eta goes to 0, this distance, eta goes to 0, then the only thing I'm left with are the two lines, 1 and 2. I can again consider the top line is just E dotted with some length. Okay, I don't even need a dot again. So what is E dot that? Okay, now since the integration is around a loop, we have that the top line and then the bottom line above, below, is minus that dl, again because the L goes in the opposite direction now. Okay, and so in this case, all the sides 0. And I do this integral, total integral is given by E, in this case above, minus E below. That's the perpendicular sides and some dl. Okay. Now this equals to 0. For the second boundary condition, that E above equals to E below is continuous. Okay. Okay. Now, finally, we could also look at You could also look at the potential above or below. In this case, if I want potential, then I could integrate again only along the side of a loop. So for example, I could just integrate from here to here. This is just some phi above, this is some phi below. In this case, with a potential, I know that phi above minus phi below is just the integral of E dot dl. In this case, the dl is given by this infinitesimally small size. So this is just E dotted with epsilon, sorry, eta. So that in the limit, eta goes to 0. What we have is that phi above phi above. Okay? Because this one goes to 0. This here goes to 0. Okay, now let me just illustrate this further. Okay? I could illustrate this further with a sphere. Draw spheres here. Nice sphere. Okay, actually, let me draw a small. Okay. Okay, and I get blue. Okay, so imagine this is a sphere, and let's give it some stuff. So this is, has some total charge of Q. Okay. Now to make this a little bit more like an actual sphere. Wow, gorgeous. Okay, so again, I could now consider, right? I've got this charged sphere over here, and I could take a look at this particular instance and look at, okay, how does the field, right, change? What are the boundary conditions imposed by this charge distribution over here? Okay. So now what I can do is I can simply create two surfaces. One is a sphere inside, and one is considering a sphere outside. Okay, let's give that a different color. One here, one here. Okay. So now let's take a look at the sphere inside. Inside, we look at Gauss's law. So E dot ds equals Q over epsilon naught equals to 0. Right? So this is only at the surface at Q. And so for the outside, I've got the integral of E dot s equals to Q over epsilon naught. And so I can I can evaluate both sides. But this is just E dotted with 4 pi r squared. Okay, and I can get rid of the arrow over here because the surface and E are parallel to each other. And this here equals to 4 pi big R squared over epsilon naught sigma. That's just the outer surface. So indeed, outside the field, the electric field is simply given by sigma r squared over epsilon naught r squared in the r direction. And so now, if I take a look at the boundary, r equals to big R, okay, and indeed this here, big R, but at the boundary, well, I know at the boundary, I know that E equals to sigma over epsilon naught in R direction. And just within the boundary, the field equals to 0. You can see the discontinuity here. Okay? Just below, it's 0. Right at the boundary, or just above the boundary, it is sigma over epsilon. At R equals 6. Okay, so indeed, this is something that we now see an explicit example of. We have that the normal component, so perpendicular to the surface, that is discontinuous. Right? We can see it here. The E field is indeed pointing in the direction of R, which is perpendicular to the surface. When it's parallel to the surface, there is no discontinuity. If it's 0 inside, then it should also be 0 outside. I hope this is clear. Okay, so now let's do exactly the same for a slightly different scenario. In this case, we want to look at the boundary conditions. Boundary condition. So we do this exact same thing, or we do something very similar. Okay, consider some surface. Okay. And now we're going to put some current, sheet current density. Okay. Just roll them out here like this. And imagine this is some K. Okay, so this is there's some current per unit surface flowing through. And again, I know the two things that I want to consider. First, I want to consider, putting some box around the surface, and I could do a loop like, that goes along with the surface, goes down through the surface, goes back along the surface, and then goes back up. So I'm going to give you 3 minutes here to see if now for yourself with the example that we've just seen before with the electric field, whether you can deduce boundary conditions for the magnetic field. Okay, give you 3 minutes. We'll come back at 6:10, and let's see if you can, you can consider these two things and come up for yourself with the boundary conditions for the magnetic field. Okay, 3 minutes. Okay, back. Um, who can tell me the boundary conditions for the magnetic fields? Anyone want to give it a go? Okay, let's see if we can arrive at this. Let me take one step and see if you can at least finish it off. So let's consider, in color. Let's consider again some box that I'm drawing like this. This, this, one box. Okay, like this. Box. And for the box, I know that I take the integral of b ds equals to 0. Again, letting the height of the box go to 0, this basically means that the perpendicular component minus the perpendicular component below equals to 0. So the normal component equals to 0. Now, in a loop sense, I can actually build two loops. I can have the loop cut through like this. I can draw one loop like this. We need to learn how to draw this like this. That's one loop. In which case, the current is piercing through the loop. But I can also draw a loop that goes along with the surface like this. Along with the current. But it doesn't make a difference whether I'm drawing the loop that then cuts through current or whether I draw one that is along with the sheet current. Now, we can now use Ampere's law to get the right answer. So now the loop, and this is just cuts through a, in which case integral simply mu naught of I enclosed okay. This is just how much there is for me to enclose, which I can simply write as mu naught k L. In this case, the integral is just b above minus b below this times L. And this here, this is the one that cuts through, and I can just get rid of the two L's. But the same loop that is along, for that there is no current, right? The loop does not cut through any current, and so I can see the B along and above minus B along, cut below equals to 0. And ultimately, and this is something that you can check for yourself, a bit smaller so I can get the full screen in. So here, indeed, it is that the B above minus B below equals to mu naught A cross n hat, right? The direction of the surface. And so if I take the direction of the surface like this, and k is in this direction, so k in n equals the one that then is perpendicular to both K and N. It's the one that goes, down in this picture, down along the field. So again, just by simply looking at, the box around the surface or two different loops, we can come to the conclusion about what the boundary conditions are for the magnetic field. Okay. Okay. Now let's take a quick example. Take a look, and let's see if we can make a very simple example. Here we've got some solenoid going around like this, all the way around. And we can ask, okay, what is the inside? The inside, the outside. Okay, so something that has a lot of coils. So we know that the inside simply mu naught Ni in the Z direction, where N is the number of windings that you have, and I is the current that goes through each individual wire. This is an example you should have seen in the exercise class. Outside, you can also show that V equals 0. So if I now take K, right, which is the surface, which is the surface current, which I can just write Ni phi, I direction, right, loops around. Actually, let me call this theta. I'll introduce symbols. N hat itself is just R hat, right? The surface, normal to the surface, is in the radial direction. And so these two combined gives me that K hat N hat, arrow here, equals minus mu naught N I in the Z direction. So indeed, here B above minus B below the surface. Again, this surface is now, outside versus inside of this solenoid, equals to mu naught N I Z hat. Okay. So just to close out, okay, we've started with showing the importance of boundary conditions in solving the Poisson equation or the Laplace equation, right? And that's going to be pivotal. And so this time what we've done is we've actually specifically looked at what are the boundary conditions if I know, for example, some surface charge, or if I know that there's some surface current. And then I can deduce the boundary conditions that are there at that particular surface. Okay? This will be the kind of the startup initial thing that we then need in order to consider what we call boundary value problems. And by looking at the system and by looking at where are the charges or the currents distributed, we ought to be able to obtain the boundary conditions for the electric field and the magnetic field. Okay, so this closes the discussion for today. Let me see if there are any questions or comments at this stage. Okay, now we can go back to the question that was asked by Ko-Ip Choi. And that's the question. If the field is due to sigma on the surface, why the field lines above and below are not pointing in the opposite direction? They are pointing in the opposite direction. Right? That's why there is a discontinuity, or there could be a discontinuity in terms of the electric field. Okay? If it goes, if it points in the same direction and the magnitude is the same, then you wouldn't have a discontinuity. But discontinuity could also be due to the sign flip. Does that answer your question? Okay. Oh, here. Okay. Thanks. Good. Okay. Are there any other questions for the recorded part? Before I stop the recording and then open up the floor for the non-recorded questions. Okay. Going once. Going twice. And okay, just in time. Harry says there's a small mistake on slide 4. Okay. Slide 4. Let's see, where do you think the mistake is? Up a little. The red circle part should be Y. Very good. Very good. I am positively amazed by how you guys can spot these tiny mistakes. Very good. If I could, I'd be giving you some candy right now. Very hard to share candy electronically. Okay, any other questions or comments for the recorded part? Going once? Twice? And stop the recording.